In this video, we're going to be talking about the Hofmann elimination reaction. Now, if you haven't done so already, I strongly encourage you to watch the video on the Cope elimination reaction by clicking on the link over here, because both of these reactions, they do have their similarities, but they also have various key differences that you should be aware of so that you can approach these reactions in the right way in your OChem classes. So before we get to the differences that the Hofmann elimination reaction has with the Cope elimination reaction, let's just talk about a similarity between them. So the similarity is that the Hofmann elimination, like the Cope elimination reaction, it is a concerted reaction, which means that all of the bond breaking and all of the bond formation takes place in a single step. It takes place in one step, okay? So now that we've covered that similarity, let's go to the key differences. So for the Hofmann elimination reaction, it actually involves anti-beta elimination. And remember that in the Cope elimination, we had syn-beta elimination. So for anti-beta elimination, there are these two groups on the molecule. They are both beta to one another, okay? So when they leave, the double bond forms on the molecule. And these two groups that leave the molecule, they have to have opposite stereochemistry because we're dealing with anti-beta elimination. So since they have to have opposite stereochemistry, one group is sticking out of the page and the other one is sticking into the page. Now let's just briefly go back to the second example I covered in the previous video for Cope elimination. Let's say we had this molecule and we were dealing with an anti-beta elimination. That would make it a lot more difficult and subjective because do we make this group sticking into the page or out of the page, or do we make this group sticking into or out of the page? It's a lot more confusing, it's a lot more subjective, which is why for these types of reactions, you tend to see them more with the Cope elimination reaction and not really with the Hofmann elimination reaction, because if you were to use a Hofmann elimination approach, then that would just make it more confusing when you solve these specific types of reactions, okay? However, there are various reactions that you can cover with the Hofmann elimination, and we will also cover two examples of the Hofmann elimination reaction in this video. So we covered anti-beta elimination. Another key aspect of the Hofmann elimination reaction is that it attacks the least hindered hydrogen atom. Now, least hindered is the same thing as saying most exposed. So it's basically least substituted, least hindered, most exposed beta hydrogen atom. So beta hydrogen atom. Once again, least hindered, least substituted, most exposed. Remember that in the Cope elimination, we attacked the most hindered, the least exposed, the most substituted beta hydrogen atom. For the Hofmann elimination, it's actually the opposite. Okay? And speaking of opposites, the Hofmann elimination reaction is actually the opposite of Zaitsev's rule. So, Zaitsev's rule states that when you have more than one option, the major product is going to be the more substituted double bond. However, since the Hofmann elimination reaction is the opposite of Zaitsev's rule, that means when you have the option, the major product is going to have the least substituted double bond. Now, just another brief aside. So you might be asking, well, hey, does the Cope elimination reaction follow Zaitsev's rule? Because over here we had this anti, and for the Cope elimination we had syn-beta elimination. For the Hofmann elimination, we have the elimination of the least hindered hydrogen atom, and for Cope elimination we have the elimination of the most hindered hydrogen atom. So does that mean that since the Hofmann elimination is the opposite of Zaitsev's rule, that the Cope elimination reaction, it follows Zaitsev's rule instead? The answer to this is not necessarily, because for the Cope elimination reaction, when you think about, ooh, I have to follow Zaitsev's rule, it can actually be quite subjective because it all depends on the structure of the molecule. Okay, so my advice to you is don't think about Zaitsev's rule when you're dealing with Cope elimination. However, you should think about Zaitsev's rule when you're considering the Hofmann elimination, because the Hofmann elimination reaction has to have a product that opposes Zaitsev's rule, but with Cope elimination, this is not necessarily the case. There are some other sources that say that it is the case. However, it depends on the structure. Just follow the rules of the Cope elimination reaction that I covered in the previous video and you should be fine. Don't think about Zaitsev's rule, just follow the rules that I covered in the previous video for Cope elimination. Okay, so now that we have that out of the way, let's go to our first main example for the Hofmann elimination. So here we have our molecule, okay, and the Hofmann elimination reaction is also divided into 3 steps. In the first step, we add excess methyl iodide, K2CO3. Now in the coelimination, we added 2 equivalents. In this case, we add excess MEI and K2CO3. We have AgI that forms. We have OH minus over here that balances out the charge on NMe3 plus. Okay, so this negatively charged oxygen atom has lone pairs, and one of the lone pairs is going to attack. Now in the second step, you add Ag2O as well as H2O. And in the third step, you add heat. And as a result, like in this case, you form the least substituted double bond, and these are your side products. So how do we get this? So again, just like we did in the previous video, we're going to divide each step into its respective chunks, into its respective components. So here we have our starting material, and we're going to add excess methyl iodide as well as K2CO3 to help with the addition of the methyl groups. So when you add the excess MEI, what basically happens is that nitrogen actually has 4 bonds now. In this case over here, nitrogen has 3 bonds in a lone pair. Here, nitrogen is going to have 4 bonds. It's going to have this bond over here like it had over here. It's now going to be bonded to 3 methyl groups. So as a result, the nitrogen atom is positively charged. And what about the iodine? Well, the iodine is going to be there, the negatively charged iodine, so that it can balance out the charge. Now, when you add the Ag2O and the H2O, what's going to happen is that the I minus is going to go with Ag. So now we're going to form AgI. We're going to form silver iodide, okay? However, we still have NMe3 plus, but instead of I minus, now we're going to have OH minus, all right? Because the negative charge balances out the positive charge. And now we're going to have beta elimination. Now, remember that in the video for coelimination, I said, when there is stereochemistry defined, then you absolutely have to worry about the syn part of syn beta elimination. However, if there is no stereochemistry defined in your problem, in your starting material, then you don't have to worry about the syn, you only worry about the beta elimination. That's a similar approach in this case. Here we don't have any stereochemistry defined. Therefore, for anti-beta elimination, well, anti isn't really relevant because we don't have any stereochemistry shown in our starting material. So as a result, we only focus on beta elimination. Beta elimination has to happen, and the least hindered beta hydrogen atom has to be removed, and we also have to have our considered step as well. So what's going to happen is the following. One of the lone pairs on the oxygen atom is going to attack a beta hydrogen, and then the covalent bond is going to go over here. So this is our double bond that's going to form. However, since carbon has to have 4 bonds to be stable, these electrons are going to get pushed to the nitrogen atom so that we form a lone pair on the nitrogen atom. So here we have our double bond, we have AgI from before, we have NMe3, okay, and then we have H2O because the oxygen grabbed this H atom. So you might be wondering, well, why do we choose this beta hydrogen? Because once again, this is our alpha carbon. It's directly attached to our NMe3 plus group, and then all of the carbon atoms that are next to or attached to the alpha carbon, they are beta carbons. So this is a beta carbon, this is a beta carbon, and this carbon over here is also a beta carbon, okay? And all of the hydrogen atoms that are bonded to the beta carbons, they are beta hydrogens. So again, remember, for Hofmann elimination, you have to remove the least hindered, the most exposed hydrogen atom, which means that you have to remove the least substituted hydrogen atom. So how do you know if the hydrogen atom is the least substituted? It is attached to the least substituted beta carbon. So look at this beta carbon. This beta carbon is only bonded to 1 other carbon. However, this beta carbon is bonded to 2 other carbons. This beta carbon is bonded to 2 other carbons. Therefore, this is the least substituted beta carbon, which makes this the least substituted, the most exposed, the least hindered beta hydrogen. So this is the beta hydrogen that's going to be attacked. And just remember that this is a methyl group, so there are going to be 2 other hydrogen atoms, but you can attack any one of the 3 beta hydrogen atoms because they are all equivalent, okay? So that's how this example works. Let's go to our second example. So here we do have stereochemistry defined, therefore we do have to worry about the anti part of anti-beta elimination. We not only have to make sure that beta elimination occurs, we also have to worry that anti-beta elimination occurs, okay? So here we have our starting material. When you add excess MEI and K2CO3, these H atoms are going to be replaced. However, nitrogen is also going to have a fourth covalent bond to another methyl group. So now nitrogen is bonded to 3 methyl groups. We have N plus Me3 and then I minus to balance out the charge, just like in this example over here. Now when you add Ag2O and H2O, the least hindered, the most exposed, beta hydrogen. So why does this occur over here? Well, remember that this is the alpha carbon because this carbon atom is bonded to the NMe3 plus group, and then all of the carbons that are directly attached to the alpha carbon, they are the beta carbon. So this is a beta carbon and this is also a beta carbon. Okay, so this beta carbon actually has no beta hydrogen, so you can't really attack that. However, this beta carbon right here, it does have one hydrogen atom. Okay, so this is the only atom that you can actually eliminate in this case. Now, keep this in mind. Here, this beta hydrogen atom is pointing into the page. Here, this NMe3 plus group, it's pointing out of the page. These two groups, this one and this one over here, they are anti to one another. Therefore, these two groups can be eliminated. The lone pair on the oxygen atom can grab this proton, then this bond over here can be kicked over here to form the double bond, then these electrons over here can be pushed onto the nitrogen to form a lone pair. And then we add our heat, and once the heat is added, we have a double bond, just like I showed here. We have NMe3+, we have H2O, and we have AgI. And also, just keep this in mind. What if I had a molecule like this? What if I had this? So I have my NMe3 plus OH minus over here, okay? And then we had, let's say we had this. We had our ethyl group over here, but this time the ethyl group is pointing into the page, and our hydrogen atom, our beta hydrogen atom, is actually going to be pointing out of the page. These two are not anti. These two groups, they are syn. Therefore, we cannot do Hofmann elimination. We can't do it because they have to be anti to one another. They cannot be syn to one another. So just keep that in mind.